Okay, I'm going to look at a worked example of inclined planes and see if you can remember all the angles from the last video. If you have trouble with the angles in this video, go back and watch the last video. Let me hit a button here, get ready to rock so I'm not distracted. And let me, where did I put my block here? Oh, no. All right, whatever. Here it is. All right, so imagine we're in this situation. Whoops, we're going this way. Oh, there it is. There's my block. Thought I had it here. So I know this is going to seem a little contrived. I'm just trying to give you a view of this. Imagine I'm a zombie and I'm pulling a suitcase up a ramp. And I hope you agree, just by looking at this picture, it's quite possible the ramp can have a different angle than the strain. All right. And that's what I'm trying to get at. And the focus is driving me nuts. Go figure, right when I pick up all this stuff. Let me hit the autofocus. Autofocus is right as all right, whatever. Life goes on. Okay. Point being, here's a weird scenario that I'm going to ignore friction for now. And I do that by putting these little wheels on the bottom. These wheels have negligible mass, they eat up negligible amounts of energy, but they reduce the friction to near zero. So for this problem, obviously there's going to be a little bit of friction, but it's completely negligible compared to the other forces involved. So if you ever see a problem where they're like, oh, a frictionless ramp, how do you really get a frictionless ramp in the real world? Put little wheels on the bottom of your suitcase. Okay, got it. Here we go. In this problem, we're going to have a zombie pulling with some magnitude of tension T up the ramp. The ramp and the tension angle might be different. To keep these straight, this is theta, the ramp incline, and this is phi, the tension angle. So the way I draw these two symbols is theta's got a straight horizontal line, phi is a nearly vertical line. And whether you like it or not, you got to get used to this, because in a lot of problems, we're going to have different angles, and we got to be able to have multiple angles. So we got to keep them straight. These are two of the more common ones you'll see in textbooks and online. So we just got to do it. All right, let's get used to it. Now, I'm going to read this problem and figure out what we're trying to do. It's 5.9, and it says, okay, draw an FBD and list the force equations. We're going to make an assumption. I think I just said this. Friction is negligible. Negligible. And I'm going to see what parameters we're given. Tension is unknown, it says in this problem statement. So we don't know the tension, so we're probably going to try and figure this out. Phi is known, so this is a known. Theta is known. What else is given in this problem? The mass of the suitcase is m, so we know the mass, and we're told it moves with constant speed. Up the ramp. Friction's negligible. Got it. In this case, if we make these assumptions, this is actually a critical assumption. If you move with constant speed in a straight line, you have no change in speed. If you have no change in speed, acceleration is equal to zero. I want to be careful here. Strictly speaking, if you have no change in velocity, your acceleration is zero. However, if you move in a straight line, with no change in speed, that's also acceleration zero, right? Velocity is speed and direction. You can actually move with constant speed in a circle and accelerate towards the center of the circle. More on that in chapter 6. So for now, constant speed is going to mean acceleration is zero. But later on, when things move in circles, that's not going to be true anymore. So said another way, I'm going to stretch this out and say, really, we should be saying this. If you move with constant velocity, then your acceleration is zero. And that is always true. All right, good enough. Well, draw the FBD. If you want to pause the video, do it now. All right, see if you could do what I do. All right, go. Here we go. FBD. we're going to do mg straight down. A lot of times I'll put the force labels at the end of the arrowheads. That way I got room to draw stuff here and here. There's a tension. It's not parallel to the plane. It's off at some other angle. Right? This angle is phi. There's a normal force kind of going perpendicular to the plane. These arrows are not to scale. And then, is there friction here? No, friction is negligible. Oh yeah, that's right, the wheels. That's why friction is negligible. All right, so I'm going to choose to split this thing up in this way. I want to use a coordinate that matches this. Look, I know about this angle, so I'm going to choose to call this the x-axis. Could you do it another way? Sure, but this is probably going to be the easiest way. So from experience, we usually want to line up our coordinate system like this, with one axis parallel to the plane and the other one perpendicular. So that's what I'm going to do here. And now I'm going to say there's no acceleration, so I'm just going to write a is equal to 0 in this problem. That came from this statement right here. So now, look at this. This one is really easy to split up if we use this coordinate system. This one would be t cosine phi. It's adjacent to the phi, it gets the cosine. This is opposite the phi. This is t sine phi. This is why I sometimes put my labels at the end of the arrows. That way I got room to shove stuff in here. Now, mg, a common mistake is to screw up mg. Watch this. I need to use this axis and this axis. So I'm going to extend this one backwards. Watch me, but don't write this. A lot of students then say, oh, I'm going to use this. Wrong. The hypotenuse of your triangle has to be the original vector. Otherwise, you're not splitting it into components correctly. And right now, this side, or the y component, is the hypotenuse. That doesn't make sense. This is what you should do. Notice the right angle is opposite the original vector. That's how you can tell. Another sign you can tell. My components match the axes. Okay. Next, what I like to do is draw some arrowheads on here, like that. Finally, from our math from before, maybe you recall, if this is theta, this is 90 minus theta, that means this is theta. So if this is theta, 90 minus theta, because there's a right triangle there, that makes this theta, which means this is theta. Or you could remember skinny angle trick. Every other one. Now here, I guess we should be careful. We have multiple angles, etc. here. But now this side is going to be mg opposite sine. This is adjacent, mg cosine theta. In chapter 3, people got bent out of shape. Why do you put angles to the vertical? It's for this reason right here. Look, you started out with an angle to the horizontal, but then because as you go around the circle, angles get flipped around and such. No matter what you do, there's going to be some problems where your angles are drawn to the vertical, despite your best efforts to avoid that. And that's why I did that. I hope that makes sense now. And just to clean this up, now I can tell, oh, I could label this mg over here because I could tell what that is, and I could put this tension over here just because I can see it a little bit better. That's just me. I've got my force equation, or sorry, my free body diagram. Now I could proceed to draw my force equations. Let's rock this out. How about sum of forces in the x? Let's do that. In this case, I'm going to grab an x force. T cos phi. That's positive. If you want to try and finish the rest, pause the video and then check and see if you got the same as me. Here we go. T cos phi, that's the positive. Now I'm going to do the mg sine. That's negative, right? Negative. Theta, that's a theta. This is a phi. Oh boy, I better pay attention. In this particular problem, sum of forces equals ma. A is 0. Maybe I'll just write it this one time. max But normally people don't even write that. They'll just write zero. So if you have no acceleration in the x, you just say, alternatively, you could say the lefts equal the rights or vice versa. Right? So we could say the positive forces equal the negative forces in the x direction. That's what I did here. Sum of forces in the y. Well, in this case, again, pause the video, check it out. Here we go. I'm going to go positive, positive, negative. G cos. Again, in this case, normally I wouldn't do this step. I just say, oh, it's zero. But just to show you where that zero came from, I feel like it's worth doing that this time. And again, a lot of times, instead of writing it this way, I probably would just skip straight to this. T sine phi plus n, the ups or the positive y's equal the downs. All right. And here's a practical force problem strategy, right? A lot of times when you get these problems, you're like, oh, the problem's talking about tension. That's a force. As soon as you hear force, you draw the FBD, write the force equations, then read the problem and say, what am I trying to find here? Again, when you can identify there's going to be some forces in a problem, I usually draw this stuff and write this stuff, then read the problem. This helps me get a feeling for all the forces involved. So I'm going to reread the problem now and see what I'm supposed to be doing, because I totally forget. Determine the tension. Oh, because tension was our unknown. And determine the magnitude of the normal force. All right. And so in this case, I'm going to look at my force equations here. We know both of the angles and the mass. G is a given. When I check this out, I'm like, oh, I know the angle, I know the G, I know the M, I know the other angle. I've got it. In particular, I see that tension is equal to mg sine theta all over cosine phi. Now, a lot of you might be thinking, oh, can't I just make that tangent? No, this is sine of one angle, cosine of a different angle. You can't just say sine over cosine equals tangent. Is that showing up on screen there? It is. I'm going to write it up here just in case you can't read that. Sorry, trying to squeeze that in there. So now I can erase this and have a little bit more legibility. So all I did was I used this equation and rearranged it in solve for t. Give me a second here. I'm going to try to squeeze that in there. Okay. And then I'll just clean up that G and that's that. All right. So once I get that tension magnitude, I could also get the normal force magnitude from this equation. N is equal to going to be mg cosine theta minus t sine phi. Well, I know what t is. I could plug this garbage into here. And you know what? I'm going to do this on the other board. I tell you what, it's going to take me a second to rewrite these equations over there. See if you could beat me to the punch. See if you can solve for n. I'll move the board over in just a second. I'm just rewriting some equations real quick. I'm going to rewrite this one. Okay, I'm going to switch boards. Keep going, try to beat me. Go, go, go. Come on, board. Come on. All right. So now all I'm going to do is plug this junk into here. At this point, you could actually use this sine over that cosine using the same angle, gives me a tangent. Also, I could factor out an mg, and this purple's dying, so I'm just gonna switch to black here so you can read it better. There's an mg that factors out, cosine is left here, and that's cosine of theta. There's a sine theta here with a minus sign from right here, and this is a tangent phi. So the idea is, if you really know the mass, g, and the angles, you can figure out the normal force. Got it. That's the example. Let's go back to the picture and see if there's anything else to kind of review here. If you don't know how I got this angle, go back and watch the previous video, but in general, strategy, sketch of the problem, free body diagram of the problem. You may need to use your sketch to do a little geometry. Fine, figure out some angles, then write your force equations. Read the question, solve for something. Done.